Okay, we're in section 8 of the notes, and we're going to cover the material that we just. I'm sorry, we're going to go cover examples that pertain to the lecture that was just presented. So we're going to do the examples in section 8.2. What's important? You paid attention during lecture, have some understanding what we presented to you. You need to reinforce this by watching some examples, and then after that, you need to study that material and then do examples on your own. And we provide opportunity for that by doing the assignment and the homework. All right. So it's important that you study before you try to do assignments, including any web assignments that are being given to you. So let me go to the whiteboard and we'll start doing the examples one by one. So give me 1 second to switch over. Shouldn't take too long. And let's go one step at a time. So first step is example number 1. Now looking at it, certainly if you recall back to when you took Math 120, that your teachers probably told you that it's not a good idea to look at functions that are unfamiliar to you. So if you can make them familiar, that would be a good thing. So I'm going to try to make this look familiar to me. And what does that mean? Cosecants should be written in terms of signs. So write this over here, limit as x goes to 0. And we're expecting to see some work on exams, by the way. So I'm going to say the cosecant of 8x is really 1 over sine of 8x. That's much more familiar to me. Times, well, cosecant of 4x on bottom would be like the sine of 4x on top. All right, so this is good news. I got it in a familiar form. Unfortunately, I can't do that limit because I have a 0 over 0 with no cancellations. So I'm going to say this probably pertains to this problem over here. The sine of theta over theta, the limit as theta goes to 0 is equal to 1. Again, I want to emphasize this over here. What are we saying? We're saying theta is going to 0. So the argument of the sine function must be the same thing as the bottom. What am I noticing over 8x? So what do I need at the top? I actually need an 8x. I'll write that down for you. If I do that, I need to put an 8x over here. All right, let's look at this guy over here. Well, this is 4x. I need this to be 4x. They'll be going to 0 at the same exact rate. Put a 4x there, I put a 4x over there. You should convince yourself that what we have now is we have 3 limit problems to do. If those limits exist, we use limit laws. This guy is 1, this guy is 1, this guy is 4 over 8. And what's 4 over 8? It's 1/2. All right, done. Next one. Next one says evaluate using squeeze theorem. They give me a picture over here, and let's talk about what the pictures are. The first picture, if you look at it, it says it's 9 minus x squared. Well, I think you can do that. But this picture over here is a picture of, excuse me, y equals 9 minus x squared. This is clearly labeled in the diagram. Let's do the last picture. And the last picture is this one over here. And again, they're clearly labeling what this is over here. This is the picture of y equals the absolute value of x squared minus 9. All right. What's in the middle? It's the picture of the function. All right. Let's put this down. And I'm going to, draw it in for you. The function looks like this over here. There's a hole at 3. And it goes up like this. All right. So someone says, what do they want me to do? They want to use a squeeze theorem. So what do I notice? Let me write this down for you. So it doesn't have to be true at 3, by the way. So I'm going to say for all x except at 3, that this inequality holds. And what inequality holds? Well, look at the picture. This picture here is always greater than or equal to this picture here. It's always greater than or equal to this picture here. And this picture here is always less than or equal to this picture over here. So let me write that down for you. So I'm going to say 9, let me go back to black ink. 9 minus x squared is always less than or equal to x squared minus 9 times x minus 3 over the absolute value of x minus 3. Whoops. Okay. By the way, this is true for all x except at x equals 3. I'm not worried about that. All right, what am I worried about? I'm worried about a limit now. So I'll take a look at the limit. So limit as x approaches 3, right? Yeah, we want 3 of the lower guy. Well, that's really simple. What's that limit going to be? 0. Let's look at the limit of the guy on the top, though. That's going to be limit as x goes to 3, x squared minus 9. That's also equal to 0. What do I know now by the squeeze theorem? Squeeze theorem. I know the limit of the middle. What's that going to be? X goes to 3, x squared minus 9, x minus 3 over absolute x minus 3 equals 0. We know that, all right, by squeeze theorem. So let's just go through what's written down over here for you. You know, certainly we are discussing it. What I discussed it, I like to look at the pictures that were provided to me. I'm convinced looking at those pictures of this inequality over here, which is written down for you. I'm also going to claim that you probably should be graphing things out on your own. And what I mean by that, using technology, if you have to, or just using your knowledge of how to graph, that's fine too. The limit of that bottom function was 0. The limit of the top one, these are the bounding functions, is 0. So by the squeeze theorem, ST, that limit is equal to 0. All right, let's go to the next one. And again, a lot of students look at these and say, I'm going to memorize these things. We're not looking for you to memorize anything. We're looking for you to reason through this. And what do I know? This has something to do with this limit over here. The rate of the top argument theta and the bottom argument has to be the same. And this is not the same, by the way. So I got to do that. Limit x goes to 0, sine 4x. Well, I got to put 4x over here. Has to be. It's not equal though. So I got to get it to be equal. So it's going to be 4/3. I hope you'd agree that these things are now equal. Do I know this guy's limit? The first factor, it's 1. So it's 1 times 4/3. So it's 4/3. All right. Work is down over here for you. All right. Evaluate using a squeeze theorem. And again, they're providing pictures. Let's just talk about it. And it's I'm not saying it's easy, but I'm looking at this and getting a better idea of what they're doing over here. And let me go through that with you. They got this lower guy here. That's that picture there. Let's see, I could graph that out, right? Then they got this upper guy here. That's that guy over there. Then they got the middle guy. There's no way I could have graphed that by hand, by the way. But I hope you get an idea that this middle guy is in between these two guys here. That this guy here is always above this one, and this guy here is always less than that one, less than or equal to it. All right. So what do I got? I got an inequality now. All right. I got an inequality. What's the inequality going to be? Let's write this down. Minus root x. I'm sorry, minus the absolute value of x is always going to be less than or equal to x times sine 1 over x. So I'm going to say this is true for all x, except x equal 0. That's not going to apply there because the function's not defined there. And then I said, you get this over bound over here. What do? I have my squeeze. I look at a limit. Limit, by the way, we're going towards 0. Yep. X goes towards 0. What's that going to be? 0. I look at the upper one, limit. That's also 0. So by squeeze theorem, what do I know? The limit of the guy in between. Is also equal to 0. Again, the picture kind of looks like that too, right? Let's go through that. Wrote the inequality down, left and right limits, did that, conclude that the limit of this thing is also equal to 0. Let's look at number 5, relatively simple question. A lot of people put a lot of effort into these things, but again, I'm going to go over it with you. And what I'm going to give you, the cosecant is very unfamiliar to me. So what do you get? Limit, x goes to 0 from the right. That would be sine. Well, sine of what? Well, sine squared of x and then x squared. All right, let people, they try to see things that are not there. I can do this limit. What's the limit of the first guy? 0. What's the limit of the second guy? It's also 0. What's this going to be? 0. All right, bingo, done. Okay, here we are. We're at an interface now. What's the interface? What some students don't entirely understand at this point. You need to study. That may include reading a textbook. It may include forming a study group, whatever works for you, but you need to study what was presented to you. What was presented to you? The squeeze theorem. After you do your study, then you got to see is, can you do what's expected of you, which is problems related to your study. Can you do this homework? Again, from personal experience, I know what happens to a lot of students to say was, well, I'll just, I understand you're doing. I'm really, they'll often say, yeah, I understand everything you've done. And then they get to the exam and they've done no study and no work, but they've understood everything that I've done. And then they realize on exams, they really understood nothing because they can't get any of the questions right. And that's unfortunate. So here's the deal. You need to study. In some senses, we're really not teaching calculus. We're teaching skills. The skill we're teaching is that study is a very important thing to do before you try. But you need to start to try. But before you try, you need to start to study. Study, then try. Thank you.